We ended last time with the following, and I called this the geometric series, that 1 over 1 minus x is equal to the sum as k goes from 0 to infinity of x to the k. And then I made this comment that this is only equal for absolute value of x less than 1. Okay, well, I'm going to use this in a moment, but let me just say, as of today's discussion, here in red, we will ignore the comments about radius and interval of convergence right now. This is something we will come back to. Really, it's best if we build the techniques of convergence for a series of numbers and the tests that we can use. Then we will come back to this. So our goal today is not to solve where a certain power series converges. That's coming later. What we're going to do is take a known power series. Here is one that's known, and we know ones for e to the x, sine, cosine, things like this. I'll write a few more. And then use it to build another power series. Okay? Now, so this section, well, manipulating power series. That's how I think of the title. Okay, so I'm going to start with this from last time. And immediately, what do we see? We see the following, that x cubed over 1 minus x. Well, I don't need to start taking derivatives, which would be, well, the first one would be a quotient rule. Then they're going to get more and more complicated. Immediately, I use this. So this is x cubed, the sum k equals 0 to infinity of x to the k. Now there is no k here. Bring it inside the sum. And we see we get a x to the, if we add exponents, we get k plus 3. Like this. Of course, we could re-index if we wanted to, but it's fine like this. Okay, well, this is a power series for this function. And then let's do another one. 1 over 1 minus 3x. This equals, okay, well, this is not just multiplying by a power. This would be function composition, okay? Where instead of everywhere here you see an x, put in a 3x. So this is a sum, k equals 0 to infinity of 3x to the k. Now you don't want to leave it like this. This is not the way we think of power series. If I make a little side box, what is a power series? Well, this I mentioned maybe 2 videos ago. It's a sum of ck x to the k, okay? Which means you want to have, if you start with something like this, to get it in the form of a power series, you want to have coefficients times powers of x, okay? And we almost have it here. Again, this is properties of exponents. So this is 3 to the k, x to the k. Now you see it's coefficients times powers of x. So immediately, without taking any derivatives or using the definition, for example, we have power series representations. Immediately, maybe I'll write it above, we have power series representations for these functions. Tations. Okay. I'm not sure where to put the hyphen. Representations is what I meant to write. So we have that this equals this, that this equals this. And what I did was I multiplied this, which was a known power series, by a power of x. Or in this case, I composed. Okay? And this is the whole strategy of today, or the goal of today's lesson, is to as I mentioned, take a known power series, manipulate it, and we get a power series for something else. We know e to the x is a sum, k equals 0 to infinity of x to the k over k factorial. And we know the sign of x. These are two power series we know. In fact, these converge for all x. To infinity, this is minus 1 to the k. Then we had an x to the 2k plus 1 divided by 2k plus 1 factorial. Now, okay, what else can we do? We talked about composing. We talked about multiplying through by a power. Well, we can add. Well, but I'll do something a little bit different. So if I want, let's do this. E to the x plus 5. This would be, maybe I will write out some terms. Here, this is 1 plus x over 1 factorial plus x squared over 2 factorial, like this. X cubed over 3 factorial. Let's write out some terms here. This would be 1 plus x plus 5. Well, I don't have to put over 1 factorial. I just did so that it matches. X plus 5 squared over 2 factorial plus x plus 5 cubed over 3 factorial plus x plus 5 to the 4th over 4 factorial. Okay, this is now, well, it's a power series centered at minus 5 for e to the x plus 5. Again, it was composition. And similarly, I can do the same for sine of x plus 5. Well, maybe I should write some terms out here because I'm about to add. We can add power series as long as they have the same center. This is what I will do here. So let's write out some terms here. The first one, when k equals 0, we get, let's see, x over 1 factorial. Then we have a minus x cubed over 3 factorial plus x to the 5th over 5 factorial minus, like this. Okay. Now let's compose with an x plus 5. So we have an x plus 5 over 1 factorial minus x plus 5, cubed over 3 factorial plus x plus 5 to the 5th over 5 factorial minus x plus 5 to the 7th over 7 factorial, like this. Okay, these are now power series representations for these two functions centered at x equals -5. Okay, like I mentioned, I just compose with an x plus 5. Now, let me erase up here, and I'm going to take them and add. And we will get a power series representation for this plus this. This is another thing that we may do. So we can add power series term by term. We can multiply through a power series by a power of x. Well, I should say, if you have a power series centered at a, you can multiply through by a power of x minus a, like this, and you get it's a transformation, it's a new power series manipulation. We can't compose. Okay, add term by term, subtract term by term, like this. And then after I finish the example, we'll get to some more things we can do. So then the sine of x plus 5 plus e to the x plus 5. Well, let's write out, you see, I'm going to have some things are going to be a little different. Let's write out, I'm going to write this with, say, 3, 4, 5, maybe 5 non-zero terms followed by a dot, dot, dot. So here, the first non-zero term is 1. Then I have a 2x plus 5. Okay, then, well, here's the only part with x plus 5 squared over 2 factorial. But then if you notice, when I add these two, this one and this one, they add to 0. So I do not have a degree 3 piece here. Then I just get a x plus 5 to the 4 over 4 factorial. This is 1, 2, 3, 4. I'll do, well, the next thing here, maybe I'll write it so that we can C, we would just have an x plus 5 to the 5th over 5 factorial. When I add these, I'm going to have 2 of them. So I'm going to have a 2x plus 5 to the 5th over 5 factorial. And, well, this would continue. I would get a x to the 6th over x plus 5 to the 6th over 6 factorial coming from this. The to the 7ths would cancel like this, but I have 1, 2, 3, 4, 5 non-zero terms. I will stop here. So this is a power series representation for the sum of these two functions centered at x equals -5. Okay, now I mentioned we're going to do more. So far we can add term by term provided we have the same center. Multiply through by a power. Compose. Okay, fine, wonderful. And these are powerful tools. But some other things we can do. So we can also do the following. We may differentiate a power series term by term. And we may integrate a power series term by term. And, well, the derivative of the power series, you take the derivative term by term, it will equal the derivative of the function, like this. If you integrate term by term, it will be an antiderivative of the function, like this. And, okay, this is one reason why power series are so incredibly important, because there are many functions out there, for example, okay, term by term, that we cannot have elementary antiderivative of, meaning you cannot express antiderivative in terms of a finite sum of things we know. But if you find a power series representation for the function, you may integrate the power series term by term, and now you have a representation for the antiderivative. It's just this infinite sum. Okay, but this is the power of power series. It comes right here, integrating and differentiating power series. Let's write what I mean. So if I have f of x equals, I'm just going to clarify these two, then we will do some examples. If a function equals of ck x minus a to the k. This is our general form of a power series, like this, centered at a. Well, what's the derivative? So the derivative equals, okay, don't let all this scare you, right? Because this is a function of x, this is a function of x, and this is the easiest derivative ever, but people get scared with this big sum. They see some complicated CKs, and then everything goes out the window. But as I mentioned when I was getting excited up here, this is the reason we love power series, because wouldn't your life be easy if all you had to do was differentiate and integrate polynomials all day long? Yes, it would. And this is just a polynomial. So here, the derivative. Well, I'm going to write a sum. I will do my, let me try another black. I will write the indices in a moment. But this is a number with respect to x. Write it down, okay? Then, how do you differentiate x minus a to a power? Well, we bring down the power, x minus a to the power minus 1. This is just power rule, polynomial, okay? It's not as complicated as people tend to make it. Okay, bring down the power, x minus a to the power minus 1. Now, with the derivative, you have to be careful. Let me write in green what is not right. You don't want to keep this here, because this is no longer a power series as written. You see, if you evaluate at 0, you have a minus 1 power. That's not polynomial. Polynomials, the lowest power you see is 0, 1, 2, 3. Then we keep adding. We never want to see negative powers like as an exponent in a power series. So we must just progress this by 1. And now you see the lowest degree that's there is k equals 0. Okay, well, so if you have a function represented in a power series, then the derivative is this. We may differentiate, that's what this says, a power series term by term. And similarly, maybe I'll write it over here. If you want an antiderivative for your function, okay, well, how do we integrate a polynomial? Add a power, divide by the higher power, except don't forget plus c. So I'll put the c here, and then this one we keep as 0, okay? And then the ck, leave it alone. The only thing here that has an x in it is x minus a to the k. Add a power, divide by the higher power, like I was saying. So we have x minus a, add a power, divide by the higher power. Okay, and this will be the power series antiderivative for the function. Okay, now, for some reason, people tend to struggle with this, and people tend to make this section hard, integrating differentiating power series, and it's hard for me to see why, because, well, I do understand why it's usually all of this stuff that scares people off. Notation, the coefficients, but please just keep it straight in your head, okay? When you write this, ignore this. It is x minus a to a power, okay? Add a power, divide by a higher power. Now you have antiderivative. Bring down the power, x minus a to the power minus 1. Now you have the derivative, okay? Now we will do some examples. I'm going to start with this example. Most problems I will do in summation notation, but for this first one, I will do it by writing out the terms. You can work either way, summation notation or writing out the first, say, 5 terms. But in any case, this is kind of a warm-up because what I'd like to do is I would like to take the derivative. Okay, well, we know what the derivative of sine is. It's the cosine. But let's see this through the power series. So what we should see here when I differentiate term by term, right? This is what I said. You have a function. You take the derivative of the function. This will equal, well, you take the derivative of the power series. So we know the derivative of sine cosine. I should see the power series representation for the cosine when I differentiate term by term. Okay, here we go. Okay, for each one of these, it's a power rule. So I bring down the power, x to the power minus 1. Bring down the power, x to the power minus 1, like this. And then here, and finally, my 5th term, like this. Okay. Well, let me make an observation about the factorial. I might have said it before, and I'll probably say it again, but it's an important observation. I'll put it in a box over here. What do we know? N factorial is n times n minus 1, 3 times 2 times 1, right? And everything here, this part, you see n minus 1 factorial. So n factorial is n times n minus 1 factorial, okay? Now, what I'm seeing here is something like a n over n factorial. So if I take a n over n factorial, this is n over n times n minus 1 factorial, and you see this is 1 over n minus 1 factorial. So for example, 3 over 3 factorial is 1 over 2 factorial. Like this, comes from this. Well, this holds, for example, n needs to be bigger than or equal to 1 integer. Then this will work. Okay, So let me use this box to simplify here. This is 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial. Do you see the cosine? I hope so. Plus x to the 8th over 8 factorial minus ... This is the power series. Well, this is the Maclaurin series for the cosine, okay? So in fact, you know, even if you didn't know the derivative of sine was cosine, if you just knew their power series representations, I have sort of proved that the derivative of sine is cosine by differentiating the power series for the sine, and I get, well, the Maclaurin series for the sine, I get the Maclaurin series for the cosine. It's very nice. Let's practice some more of this power series manipulation, and what I will say is what we are moving towards is through this activity, we will find a power series representation for the inverse tangent function. Okay, but I'm not going to, for example, start taking derivatives, evaluate the kth derivative at 0 over k factorial. That would be the definition of the Maclaurin series, and I will not do that. I will use what we're discussing now. Okay, well, this we know, right? And now let's do some steps. So then we build from this geometric series. I can therefore state that 1 minus, like this is 1 over 1 plus x squared. This equals, okay, well, this is a composition with a minus x squared. So this would be minus x squared to the k. And as I mentioned in one of the first examples, we don't want to leave it like this for power series. We want to write it as coefficient times x to a power. And here we see we will get k equals 0 to infinity. This will be a minus 1 to the k, x to the 2k. So this is a power series representation for 1 over 1 plus x squared. And then what can we do with power series? Well, this would be equal to c plus the sum, k equals 0 to infinity. Now, this one I'm not writing out terms like I did for the sine, but this is just minus 1 to the k, recopy. Then, well, this is the term I am integrating. It's x to a power. We add a power, divide by the higher power. This becomes x to the 2k plus 1 divided by 2k plus 1. Now, this is where I said, you know, in this activity where first we start with this, we do a composition, then we integrate. You see, what is this? We know what this is. This is the inverse tangent, except this stands for, as we know, it's a set of all antiderivatives. There's a plus c there. If we want a particular antiderivative, which I do, I need to solve for this c. And we practice this, say, Calc 1, or maybe in the very beginning section of this course, where if you're trying to find some specific antiderivative, you just evaluate antiderivative that has a plus c at what value, solve for the c, like this. And this is what I will do. Okay, so, k equals 0 to infinity of minus 1 to the k, x to the 2k plus 1 over 2k plus 1. But I need to find, I'll put this in black, we need to find capital C, because this is, as I mentioned, a specific antiderivative. Well, let's just evaluate both sides at 0, which is the center. And evaluating a big power series at the center is quite easy. The tan inverse of 0 is c plus, all of these terms vanish, we get 0. So this is just c. Well, what is the tan inverse at 0? Okay, this says the tangent is 0 and you're between minus pi over 2 and pi over 2. Your angle is therefore 0. Okay, so we see C is in fact 0, and we get from this that the inverse tangent equals this as a power series. Minus 1 to the k, x to the 2k plus 1 over 2k plus 1. Okay, this is what we see from this exercise. I will make a comment that our text, it lists several Maclaurin series that you can use in this section to manipulate. And in particular, e to the x, sine x, cosine x, 1 over 1 minus x, and ln of 1 plus x. We have used at least the first 4. In fact, this one you could get by, let's see, integrating. So this one, in theory, the text doesn't need to give you. Should we do that as an exercise? Maybe we should. This is a nice activity. So we will do this. Hadn't planned on it, but if you know these 4, you can get this one. This is my comment, and let's do it. It's just like the last example. So we know 1 over 1 minus x is the sum k equals 0 to infinity of x to the k. Therefore, 1 over 1 plus x. Well, this is 1 over 1 minus x. This is the sum k equals 0 to infinity of minus x to the k, which is a minus 1 to the k, x to the k. Minus 1 to the k, x to the k. Now, if I want a power series for ln 1 plus x, look. This is super cool. We integrate because, well, I will do this first. It's very much like our arctangent that we just finished. Then, well, here, this is a sum. Oh, don't forget the plus c. Never forget the plus c. Okay. It's a sum, k equals 0 to infinity. I have minus 1 to the k. I add a power. Divide by the higher power. Well, again, this, if we integrate this, this is ln 1 plus x, except that's just one antiderivative for this, and I can solve for the constant just as I did for the arctan by evaluating at the center. So at x equals 0, look what I get. So then I will write this as I did before, solve for c, okay? And we get ln of 1 is c, well, plus 0, right? Evaluating at the center, this is 0. Well, the natural log of 1 is 0. So in fact, c is 0, and we get this Maclaurin series for ln of 1 plus x. So this is what you will see in your textbook. For example, here's an example. So how could we, for instance, use these, or one of these, I should say, to address a really real question that can come up and does come up, which is something like this. Okay, if we take the integral of 0 to 1 cosine x squared, this is one of the functions that has no elementary antiderivative, meaning you cannot write the cosine of x squared, well, its antiderivative, in terms of a finite sum of functions that we know. So we will never find this number, for example, using fundamental theorem of calculus. We could, as we know, what have we even done in this course? trapezoid rule, Simpson's rule. We can find this using either one of these or an approximation, I should say. But we also know that those take a lot of time. We have to have delta x, which would be 1 over n. And then we find this partition. And then we either have a delta x over 3 or a delta x over 2. And then we have this big sum. And those take a lot of time. In fact, what's simpler is to use partial sums of power series. Okay, so how could we use that here? Well, here is the Maclaurin series for cosine of x. This means that the cosine of x squared, okay, we just compose. So I put in x squared for this. This is a sum k equals 0 to infinity of minus 1 to the k x squared to the 2k over 2k factorial. And then, for instance, we want to not leave it like this. We want to write every power series as some coefficients times x to a power. So one more step I would take would be the following. This would be minus 1 to the k, x to the 4k over 2k factorial. This is the cosine of x squared. In fact, this is a Maclaurin series for the cosine of x squared. Now let's just write out some terms here. Okay, so when k equals 0, I get, this is a 1, this is 1, this is x to the 0. Okay, not too bad. When k equals 1, I have a negative, this is x to the 4th over 2 factorial. When k equals 2, I have a plus x to the 4 times 2, which is 8, over, this is a 4 factorial. And then I'll write a few more maybe. When k equals 3, this will be a minus. We get, let's see, this is going to be x to the 12th over, this is going to be 6 factorial. Okay, just like this. Now, if I want to use this to approximate this definite integral, I can just take the first few non-zero terms, which is a Taylor polynomial, or equivalently, it's a partial sum of this series. Now, if you think about it, even if I added this term, if I integrate, I get an x to the 9 over, it's going to be 9 times 4 factorial. This is going to be super tiny when I evaluate 1. So I might just use the first two. I'm going to use these two. So these two, well, I could even write this. This is t f of, well, it's 4. If we want to write, because I see a 4 here, of x 0, where f of x is cosine of x squared. Even though I didn't build it from the definition by starting taking derivatives, I built it by manipulating a known Maclaurin series. This is the 4th order Maclaurin polynomial, for example. Okay. Well, now you'll see how fast this is compared to, say, Simpson's rule or trapezoid rule, because I come back up here. This is approximately the integral 0 to 1 of what I have underlined. 1, oh, I didn't write the 1. 1 minus x to the 4th over 2 dx. Now this is an integral. Well, this is quite simple to integrate. This is why we love power series, because look how simple this is. Look how hard this is. And yet, these are very, very close. This one is x minus x to the 5th over 10 from 0 to 1, which is 1 minus a 10th. This is 9 over 10. Okay, so this 9 over 10 is approximately this definite integral. And the way I went about it is significantly, in my opinion, easier and faster than if I had to do Simpson's or trapezoid rule. Oh, standing in front of it, for example, okay? I'll end with one more example, and it reads a little bit different, but it's exactly the same techniques that we've been using in this video, and it's the following. We are asked to find a power series derivative and antiderivative for this. And perhaps what's different is this power series we are handed is not clearly a Maclaurin, or, well, wouldn't be Maclaurin. It's not clearly a Taylor series for anything, right? It's just a power series. And we notice here, I'll make this comment, that the center is 2 because we have an x minus 2 to the k. But these things are not just bouncing off the top of my head as the kth derivative evaluated at 2 divided by k factorial for some function that I know. But it's fine. This is a power series. It's of the form ck times x minus the center to the k. It's a more general looking power series. Okay, so, well, we can find a power series for the derivative, find a power series for the antiderivative, and I will write these in summation notation because, as I mentioned, for me, it's much easier. I don't have to write out 5 terms and integrate every single term or differentiate every single term. Writing it in summation notation, I only have to integrate or differentiate 1 term, and to me, I find that easier. Okay, so here, derivative. Well, this I discussed. I will put this later. The k factorial over 7 to the k, these are the coefficients. In fact, you can just write them down, just their numbers with respect to x. Okay? And then here is my power rule. So I bring down the power, x minus 2 to the power minus 1. And this is all there is. So what I have differentiated is just this. This is the derivative of the kth term with, these are the coefficients that come along, just like you were differentiating, well, a number times the power of x. With respect to x, that the coefficients are just a number. But as I commented when I first wrote down the derivative, you see I can't start at 0. I can't write that here because here this would have a term with a minus 1 power. That doesn't appear in power series, so I just start my sum here. Of course, if I looked at this and evaluated at 0, this thing here would make it 0. So you don't even need that term anyways, but you don't want to write k equals 0 because you do not want to have something that has a negative power in it. Okay, so when you take the derivative, just check. And if evaluating at 0 gives you a negative number, shift it up by 1 as I did. So start at k equals 1. Okay, here's the derivative. Now finally the antiderivative. We integrate. This would be c plus. Okay, then we have a sum. And then this part again, I recopy. The coefficients, I have just recopied. Then this is the only part. Maybe I will underline this in green because I used it in both. This is the only part that has an x. And when you integrate a power, add a power, divide by the higher power. Okay, so this is x minus 2 to the k plus 1 divided by the higher power, k plus 1. Maybe I'll put a parentheses just so you realize there's a product here with 7 to the k. But this is the power series for antiderivative. Well, I put the plus c, it's really all antiderivatives. And again, this was the part I integrated. Add a power, divide by the higher power, just like this.